November 18, 1943. Yokosuka Naval Air Technical Arsenal, Kanagawa Prefecture, Japan. Lieutenant Commander Minoru Suzuki stood in the early morning cold, staring at an aircraft that represented everything Japanese naval aviation had been taught to dismiss as wasteful American excess. The Grumman F6F-3 Hellcat sat inside a reinforced concrete revetment, guarded continuously by armed naval infantry. The aircraft wore faded United States Navy markings, battle-damaged scars visible across the wings and fuselage, bullet holes patched temporarily for the flight from Rabaul, where it had been captured 3 weeks earlier after crash landing in shallow water near Simpson Harbor. Suzuki had been flying fighters since 1937. He had 6 years of combat experience over China, where Japanese aircraft had dominated through superior maneuverability and pilot skill. He had studied every intelligence report available about American fighters. The Grumman F6F Wildcat, tough but slow. The Chance Vought F4U Corsair, fast but difficult to land on carriers. And now this, the F6F Hellcat, the fighter that was systematically destroying Japanese air superiority across the Pacific. The statistics were impossible to ignore. At the Battle of the Philippine Sea 5 months from now, in June 1944, Hellcats would shoot down approximately 300 Japanese aircraft while losing only 30 of their own, a 10-to-1 kill ratio. But Suzuki didn't know that yet. What he knew in November 1943 was that Japanese pilots were dying at accelerating rates against this new American fighter. The official Imperial Japanese Navy assessment of the Hellcat was brutally direct. It was heavier than the Zero, slower in a turn, less maneuverable at low speeds. Japanese doctrine emphasized that these characteristics made it inferior. Weight was the enemy of performance. Armor was dead weight that reduced climb rate and turning ability. The Zero had proven this philosophy correct for 2 years, dominating through lightweight construction and supreme agility. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But the reports from frontline squadrons told a different story. Zero pilots described Hellcats that wouldn't burn when hit, American pilots who survived crashes that should have killed them, bullets that seemed to bounce off critical areas. One flight warrant officer had filed a combat report claiming he had fired an entire 60-round load from his Type 99 20mm cannon directly into a Hellcat's fuselage from less than 100 yards. Range. The American fighter had continued flying, made it back to its carrier, and landed successfully. Japanese intelligence officers initially dismissed the report as combat stress or poor gunnery. 60 20mm explosive rounds should have torn any aircraft to pieces. The officer must have missed more shots than he realized. But then similar reports arrived from other units, different pilots, different locations, all describing the same phenomenon. Hellcats absorbing damage that would have destroyed a Zero instantly. The captured Hellcat in front of Suzuki represented the opportunity to understand why. American ground crews at Rabaul had burned the aircraft after abandoning it, but the fire had been extinguished quickly by Japanese forces. The engine was destroyed, the propeller was bent, the landing gear collapsed. But the airframe was intact enough for detailed examination, and that was what mattered. Suzuki had been assigned to lead the technical evaluation team. His orders came directly from the Naval Air Technical Arsenal's commander. Determine the Hellcat's actual capabilities, identify its weaknesses, develop tactics that would allow Zero pilots to defeat it. The future of Japanese naval aviation might depend on what his team discovered. The recovery operation had been a significant undertaking. A Japanese submarine had approached Simpson Harbor under cover of darkness on November 2nd. Combat engineers had worked through the night, attaching flotation bags to the sunken Hellcat and dragging it to a barge. The barge had been towed to a larger transport ship waiting offshore. The Hellcat had been shipped to Truk, then transferred to another transport for the journey to Yokosuka, arriving on November 15th. Navy mechanics had spent 3 days conducting preliminary assessment and preparing the aircraft for detailed examination. They had pumped water from the flooded sections. They had opened access panels carefully. They had photographed everything before touching anything. The goal was to understand American construction techniques, material choices, and design philosophy. What they found contradicted everything Japanese engineering doctrine taught about fighter aircraft design. Suzuki walked slowly around the Hellcat, noting details. The aircraft was massive compared to a Zero. The fuselage was thick and robust. The wings were substantial. Even damaged and waterlogged, the Hellcat looked solid, purposeful, built to absorb punishment. He climbed onto the wing and looked into the cockpit. The seat was surrounded by a steel plate. Behind the pilot's position, an armor plate approximately 8 millimeters thick extended from the headrest down to the seat bottom. Suzuki tapped it with his knuckles. Solid steel. Heavy. Protective. Japanese fighters had no such protection. The A6M0, the J2M Raiden, the N1K Shiden, none incorporated armor behind the pilot as standard equipment. Some late-model Zeros had thin armor plates added in 1944, but even those were minimal, barely adequate to stop rifle-caliber rounds. The philosophy was clear. Weight saved was performance gained. Protection was secondary to maneuverability. But this American fighter had been designed, from the beginning, with pilot protection as a primary consideration. The armor wasn't an afterthought. It was integrated into the fundamental structure. Suzuki's preliminary examination continued. He moved to the engine compartment. The Pratt & Whitney R 2800 double wasp radial engine was destroyed by fire and water damage, but the engine mounting structure was intact. Heavy steel plates surrounded the engine on 3 sides, protecting it from ground fire and deflecting incoming rounds away from critical components. The oil cooler, a vulnerable component on any aircraft, was protected by armored shielding. The fuel lines running from the wing tanks to the engine were armored where they passed through the fuselage. Every critical system had been designed with battle damage consideration. A chief petty officer who had worked on the preliminary assessment approached Suzuki and bowed. "Commander, you should examine the fuel tanks." Suzuki followed him to the wing center section, where mechanics had carefully cut away aluminum skin to expose the internal structure. The fuel tanks were clearly visible, but something about them looked unusual. "Self-sealing tanks, sir," the chief petty officer explained. "American design. Multiple layers of rubber and fabric. When a bullet penetrates, the rubber swells from contact with fuel and automatically seals the hole." Suzuki leaned closer, examining the construction. The tank walls were thick, far thicker than the simple aluminum tanks used in Japanese fighters. He could see the layered construction. An outer aluminum shell, a layer of vulcanized rubber, a fabric layer, another rubber layer, an inner fuel-resistant coating. "Have you tested this?" Suzuki asked. "Yes, sir. We fired a 7.7 mm round through a sample section we removed. The hole sealed itself within seconds. Fuel leakage stopped almost immediately." Suzuki nodded slowly, understanding the implications. The pilot would have seconds to bail out before the aircraft became an inferno. Many pilots never made it out, but this American fighter could take multiple hits in the fuel tanks and return to its carrier safely. The weight penalty must be enormous. Self-sealing tanks weighed significantly more than simple aluminum tanks. The rubber layers alone added hundreds of pounds. That weight reduced climb rate, turning ability, and maximum speed. By Japanese engineering standards, it was inefficient and wasteful, but it kept American pilots alive. Over the next 5 days, Suzuki's team systematically disassembled the Hellcat, documenting every component, every design choice, every material selection. They worked 12-hour shifts, photographing and measuring and analyzing. What emerged was a comprehensive picture of fundamentally different design philosophy. The aluminum skin covering the Hellcat's fuselage and wings measured 0.050 inches thick. The team measured it, repeatedly with precision micrometers to confirm. American minimum standard. The Zero's skin measured 0.032 inches, barely 60% as thick. The difference seemed small, 18 thousandths of an inch, but the implications were enormous. The thicker skin added structural strength and battle damage resistance. A single .50 caliber bullet might punch through both sides of a Zero's fuselage. The same bullet would penetrate the Hellcat's skin but might not exit the other side, reducing damage to internal systems. The wing structure revealed even more striking differences. The Hellcat used heavy internal spars with substantial reinforcement. The wing could withstand extreme G-forces during combat maneuvering without risk of structural failure. Japanese intelligence had documented cases of Hellcats pulling out of dives at speeds exceeding 350 miles per hour, subjecting the airframe to forces that would have torn a Zero's wings off. The landing gear was massively over-engineered by Japanese standards. Heavy forged steel components, robust hydraulic systems. The gear was designed to absorb carrier landing impacts repeatedly without failure. Zero landing gear, by contrast, was lightweight and delicate, adequate for careful landings, but vulnerable to damage from hard carrier approaches. Suzuki's team found armor plating in locations they hadn't expected. The windscreen incorporated bulletproof glass, thick laminated layers that could stop rifle rounds. The instrument panel had an armored shroud protecting critical gauges. Even the radio equipment was shielded with steel plate to prevent combat damage from disabling communication. The mechanics calculated the total weight of armor and protective equipment, approximately 2,100 pounds. Just the protection systems, not including the heavier structure and thicker skin. That was nearly the equivalent of the entire empty weight of a Zero fighter. 2,100 pounds of weight that did nothing to improve performance. It didn't make the Hellcat faster. It didn't make it more maneuverable. It didn't extend its range. By Japanese engineering philosophy, it was completely wasted weight that handicapped the aircraft. But it did one thing extraordinarily well. It brought American pilots home alive. On November 24th, 6 days after examination began, Suzuki conducted the critical test that would define his report. His team had fabricated a test panel representing a typical section of the Hellcat's fuselage structure. Aluminum skin, structural frame members, and behind it, the 8mm steel armor plate that protected the pilot. They mounted the panel on a test stand at the arsenal's weapons range. Suzuki personally selected the ammunition. Type 99 Model 120mm cannon shells, the standard armament carried by Zero fighters. Each shell contained 31.4 grams of explosive filler designed to detonate on impact. The Type 99 cannon was a licensed copy of the Swiss Oerlikon design. It fired at approximately 500 rounds per minute, relatively slow by international standards. But the explosive shells were devastating against unarmored targets, against Chinese fighters, against early American aircraft, against unprotected ground targets. The 20mm cannon had proven deadly. A Zero carried 60 rounds per cannon, mounted in the wing's outboard of the propeller arc. In combat, a skilled pilot might fire 2 to 3 second bursts, expending 10 to 15 rounds per burst, 3 or 4 bursts before the ammunition was exhausted. Suzuki loaded the test cannon himself, ensuring proper seating for each round. He positioned himself at the firing station, aimed carefully at the center of the test panel from 100 meters range, typical combat distance, and fired a single shot. The cannon roared. The shell crossed the distance in a fraction of a second and struck the test panel with a sharp crack. Suzuki lowered the cannon and walked forward to examine the impact point. The aluminum skin was penetrated cleanly. The shell had punched through the outer layer, detonated against the internal structure, and fragmented. But the steel armor plate behind showed only a deep gouge where fragments had struck. The plate was dented but not penetrated. The explosive force had been largely absorbed by the armor. Suzuki fired 5 more rounds, varying the angle of impact slightly with each shot. The results were consistent. The aluminum skin penetrated easily. The internal structure was damaged but not destroyed. The armor plate gouged and dented but holding intact. No complete penetration. He repositioned the cannon to 50 meters range, closer than typical combat engagement, but representing a fortunate firing solution. He fired 10 rounds rapidly, a sustained burst, simulating combat conditions. The test panel was shredded. The aluminum skin was torn and punctured. The internal structure was damaged severely, but the armor plate, though heavily scarred and deformed, remained intact. Not a single shell had penetrated completely through to where the pilot would sit. Suzuki stood in silence, staring at the battered test panel, understanding with complete clarity what this meant for Japanese fighter tactics. A Zero pilot could achieve a perfect firing solution, close to ideal range, and pour 20mm cannon fire directly into a Hellcat's fuselage. The American pilot would feel the impacts, he would see the damage. But he would survive. The armor would protect him, he would make it back to his carrier. The same burst of fire into a Zero would kill the pilot instantly. The thin aluminum skin offered no resistance. The explosive shells would detonate inside the cockpit. There was no armor to stop them. The pilot had no protection except his skill in avoiding being hit. The implications extended far beyond simple protection. Japanese pilots had been trained since the beginning of the war to aim for the cockpit when engaging enemy fighters. Kill the pilot, and the aircraft falls regardless of other damage. It was an efficient, decisive tactics. But those tactics assumed the pilot was vulnerable. They assumed cockpit hits were fatal. Against the Hellcat, that assumption was false. The armor plate changed everything. Cockpit hits that should have killed American pilots were instead survivable impacts that damaged the aircraft but allowed the pilot to escape. Japanese pilots would need to aim for different target areas. The engine, attempting to penetrate the protective shielding. The wings, trying to rupture fuel tanks despite the self-sealing capability. The tail, hoping to sever control surfaces. All of these targets required more ammunition, more time in the firing position, more exposure to the Hellcat's 650 caliber machine guns. Suzuki returned to his office and began writing his preliminary report. His hand moved steadily across the paper, forming characters that described a fighter aircraft built on principles completely opposite to Japanese design philosophy. The Grumman F6F Hellcat, he wrote, represents the American industrial and engineering approach to fighter aviation, where Japanese design emphasizes lightweight construction and maximum maneuverability through weight reduction. American design emphasizes pilot protection and aircraft durability through extensive armor and robust structure. The Hellcat weighs approximately 12,761 pounds, fully loaded according to captured technical documentation. This compares to the A6M50 at 6,005 pounds fully loaded. The Hellcat weighs more than double a Zero. Yet despite this enormous weight penalty, the Hellcat achieves maximum speed of 376 miles per hour, faster than the Zero's 300 to 33 miles per hour. This performance is achieved through overwhelming engine power. The Pratt & Whitney R2800 produces 2,000 horsepower, more than double the Nakajima Sakai's 950 horsepower. American industry has solved the weight penalty of protection through massive engine power that Japanese industry cannot currently match. Suzuki paused, considering his next words carefully. What he was about to write contradicted the fundamental philosophy that had guided Japanese fighter design for a decade. Recommendation: Japanese fighter aircraft doctrine must acknowledge that the advantage of lightweight construction is negated by vulnerability to battle damage. American fighters achieve survivability through protection rather than maneuverability. This approach allows their pilots to survive combats that would kill Japanese pilots. Over extended campaigns, this survivability advantage produces cumulative superiority, regardless of individual aircraft performance characteristics. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. He knew the recommendation would be controversial. Senior officers who had championed the Zero's design philosophy would resist acknowledging that the Americans had chosen a better approach, but the evidence was undeniable. The test panel bearing 20mm shell impacts told the story more clearly than any words could. The complete technical report took Suzuki 3 days to compile. He included detailed measurements, photographs of the disassembled Hellcat, comparative analysis against Japanese fighters, and tactical recommendations. On November 27th, he submitted the report to Captain Toshio Miyazaki, commander of the Naval Air Technical Arsenal. Miyazaki read the report in silence, occasionally pausing to study a photograph or reread a section. When he finished, He set the papers down carefully on his desk and looked at Suzuki with an expression that combined respect and concern. Your findings are thorough and well documented, Commander, but you understand the implications of what you're recommending? Yes, sir. I'm recommending we fundamentally reconsider our approach to fighter design. The Americans have demonstrated that protection and durability can produce better overall combat effectiveness than pure maneuverability. Miyazaki nodded slowly. Your recommendation will not be well received by many officers. The Zero has been our most successful fighter. Its design philosophy has guided our entire naval aviation program. I understand, sir, but the statistics from recent engagements speak for themselves. Our pilots are achieving fewer victories per sortie. Our loss rates are increasing. The Americans are not flying better tactics. They are flying aircraft that keep their pilots alive long enough to gain experience. This was the heart of the matter, and Suzuki knew it. Japanese pilot training had been reduced dramatically by late 1943. The pipeline of experienced aviators from the pre-war years was nearly exhausted. New pilots received minimal training before being sent to combat units. They faced American pilots who survived multiple combat missions because their aircraft protected them. A Japanese pilot might achieve his first victory on his 5th combat mission, if he survived that long. An American pilot flying a Hellcat might survive 20 combat missions, learning and improving with each engagement. By his 20th mission, he was a veteran, experienced and dangerous. The cumulative advantage was devastating. Miyazaki stood and walked to the window, overlooking the arsenal's runways. I will forward your report to the Naval General Staff with my endorsement. But, Commander, you should prepare yourself for resistance. Many senior officers will view your conclusions as defeatist or as criticism of decisions made by their predecessors. I'm reporting facts, sir. The Hellcat's armor plate stops 20mm cannon fire. That is not my opinion. That is measurable reality. Facts can be inconvenient, Commander, especially facts that suggest we chose the wrong path 10 years ago when the Zero was designed. Suzuki's report reached Naval General Staff Headquarters in Tokyo on December 2nd. It was reviewed by a committee of senior officers, technical specialists, and aircraft designers. The response came back within a week. The report was acknowledged as technically accurate. The test results were accepted as valid. The tactical implications were noted, but the fundamental recommendation to redesign Japanese fighters with extensive armor protection was rejected. The official explanation cited resource constraints. Japan lacked the industrial capacity to produce the massive engines required to compensate for armor weight. The Mitsubishi Ha-43 engine under development might eventually produce 2,000 horsepower comparable to American engines, but it was years away from reliable production. Current Japanese engines produced at most 1,500 horsepower, insufficient to power an armored fighter with acceptable performance. Additionally, aluminum production was constrained. Japan imported most of its aluminum ore, and submarine warfare was disrupting supply chains. Using aluminum for thick skin and heavy structure would reduce the total number of aircraft that could be produced. Military leadership preferred more aircraft with less protection over fewer aircraft with more protection. The rejection was predictable but still frustrating. Suzuki understood the resource arguments. Japanese industry was not equivalent to American industry. The United States could afford to build heavy, durable fighters because they had unlimited resources. Japan had to make difficult choices. But understanding the reasoning didn't change the fundamental problem. Japanese pilots were still climbing into fighters that would burn if hit in the fuel, tanks that offered no protection if the cockpit was struck, that would disintegrate under sustained 50-caliber machine gun fire. Meanwhile, information from Suzuki's report was distributed to combat units with tactical recommendations. Avoid prolonged engagements with Hellcats. The American fighter's durability makes it difficult to destroy quickly. Japanese pilots should prioritize attacking bombers rather than engaging escorting fighters when possible. If combat with Hellcats is unavoidable, aim for the engine or control surfaces rather than the cockpit, as the pilot is heavily protected. Squadron commanders incorporated these recommendations into briefings, but many pilots found them difficult to implement. Combat was chaotic, In the heat of a dogfight, a pilot aimed for whatever target presented itself. Training yourself to avoid cockpit shots, when that was your instinctive aiming point, required conscious effort that could cost precious seconds. Some pilots ignored the recommendations entirely. Lieutenant Tetsuzo Iwamoto, an ace with documented victories dating back to the China campaigns, stated bluntly in a squadron briefing that he would continue aiming for the cockpit regardless of armor. His philosophy was simple: shoot more accurately, fire from closer range, use more ammunition per burst, overwhelm the protection through volume of fire. Iwamoto would survive the war with 80 credited victories according to some sources, though official records documented fewer. His aggressive tactics worked for him because he was exceptionally skilled and lucky. Most pilots following his approach died before achieving similar success. The captured Hellcat remained at Yokosuka for continued study. Engineers examined every aspect of its construction, looking for innovations that could be adapted to Japanese designs within resource constraints. Some features were practical to incorporate. The Hellcat's gun sight was superior to Japanese designs. It incorporated a gyroscopic computing element that automatically adjusted the aiming reticle for target-lead angle based on the target's angular velocity. Japanese engineers studied this mechanism carefully and developed similar gyroscopic sights that entered limited production in 1944. The Hellcat's radio equipment was more reliable and provided clearer communication than Japanese radios. Some of the design elements were copied and incorporated into updated Japanese radio systems, improving coordination between aircraft. But the fundamental elements that made the Hellcat effective, the armor protection, the self-sealing fuel tanks, the robust structure, the massive engine, could not be replicated. Japanese industry lacked the capacity to produce them at scale. Japanese designers attempted compromises. The Kawanishi N1K2J Shidenkai, introduced in late 1944, incorporated some armor protection and automatic fire extinguishing systems in the fuel tanks, but it still weighed far less than a Hellcat and remained vulnerable to battle damage. The Mitsubishi A7M Repu, designed as the Zero's true successor, included pilot armor, self-sealing tanks, and a more powerful engine, but development problems and production delays meant it never reached combat units in significant numbers before the war ended. By mid-1944, the situation had become critical. The Battle of the Philippine Sea in June demonstrated the gulf between Japanese and American naval aviation capabilities. American pilots called it the Great Marianas Turkey Shoot. Approximately 400 Japanese aircraft were destroyed over 2 days of combat. American losses totaled approximately 30 aircraft. The kill ratio was not 10-1. It was more than 13-1 in America's favor. Hellcats accounted for the majority of American victories, their pilots using tactics specifically designed to exploit their aircraft's strengths. High-speed diving attacks, boom and zoom. Never slow down into a turning fight where the Zero's maneuverability advantage might matter. Japanese pilots who survived these engagements reported the same observations Suzuki had documented 6 months earlier. Hellcats absorbed damage that should have been fatal. American pilots survived hits that would have killed Japanese pilots instantly. Multiple Zeros would converge on a single Hellcat, score hits with cannon fire, and watch the American fighter dive away, trailing smoke but still flying, still dangerous. One flight warrant officer reported emptying his entire ammunition load into a Hellcat during the Philippine Sea battle. He saw his 20mm shells hitting the fuselage. He saw pieces of aluminum skin flying off. The Hellcat's engine began smoking, but the American pilot continued flying, maintained control, and made it back to his carrier over 70 miles away. The warrant officer landed back aboard his carrier with empty guns and nothing to show for the expenditure of ammunition. These reports vindicated Suzuki's findings, but vindication meant little when pilots were dying. By late 1944, experienced Japanese naval aviators were becoming rare. The training pipeline couldn't replace losses. New pilots were being sent to combat units with barely 100 flight hours total, sometimes less. They faced American pilots with hundreds of hours of experience flying aircraft that protected them even when they made mistakes. The mathematical progression was inexorable. Each combat engagement, Japan lost a higher percentage of participating aircraft than the Americans. Each loss removed a pilot who could not be easily replaced. Each American victory created a more experienced pilot who would be even more dangerous in the next engagement. The curve was exponential, and it pointed toward inevitable defeat. In January 1945, the captured Hellcat was destroyed during an American bombing raid on Yokosuka. B-29. Superfortress bombers attacked the naval arsenal, targeting production facilities and repair hangars. The concrete revetment where the Hellcat was stored took a direct hit from a 500-pound bomb. The aircraft was obliterated, reduced to scattered fragments of aluminum and steel. By that point, the intelligence value of the captured aircraft had been thoroughly extracted. Suzuki's report had been distributed. The test results had been analyzed. The tactical recommendations had been implemented as much as Japanese capabilities allowed. The physical aircraft no longer mattered. What mattered was what it represented. The Hellcat embodied a design philosophy that Japanese industry couldn't match with available resources. American engineers had solved the fighter aircraft problem differently than Japanese engineers. They had prioritized pilot survivability and aircraft durability over lightweight maneuverability. They had compensated for the weight penalties through overwhelming engine power and industrial capacity. Japan had chosen the opposite path. The Zero had been optimized for performance through radical weight reduction. Every unnecessary pound had been eliminated. Armor was unnecessary weight. Self-sealing tanks were unnecessary weight. Thick structural members were unnecessary weight. The result was an aircraft that performed brilliantly within its design envelope, but was fragile and vulnerable. That design philosophy had been correct in 1940 and 1941, when Japanese pilots were the best trained in the world, and Chinese opposition was minimal. The Zero had dominated because skilled pilots flying maneuverable aircraft could avoid being hit while positioning for killing shots. But by 1944, the situation had reversed completely. American pilots were well-trained and experienced. American fighters were fast and heavily armed. American tactics emphasized speed and energy management rather than traditional dogfighting. In this new environment, the Zero's advantages didn't matter, and its vulnerabilities were fatal. Suzuki survived the war. He was promoted to commander in May 1944, despite the unfavorable reception of his Hellcat report. He flew combat missions during the Philippines campaign and was wounded twice, sustaining injuries that ended his flying career. He transferred to a staff position at Yokosuka, where he spent the final months of the war training new pilots who would never accumulate the experience necessary to be effective. After the war, Suzuki participated in interviews with American technical intelligence teams. He provided detailed information about Japanese fighter development, tactical evolution, and the impact of American aircraft on Japanese capabilities. The Americans were particularly interested in his assessment of the captured Hellcat. Did examining the Hellcat change Japanese fighter tactics? An American intelligence officer asked during one interview, session in October 1945. Yes, Suzuki replied through a translator. We understood that American fighters were protected in ways our aircraft were not. We developed tactics to account for this. But understanding a problem and solving it are different things. We understood the Hellcat's advantages. We could not replicate them. Why not? Resources, industrial capacity, time. The Hellcat represented the American ability to build aircraft with no compromises. Heavy armor, powerful engine, durable structure, all in one aircraft. Japan could not afford that approach. We had to choose between armor and performance. We chose performance because our engines couldn't power an armored fighter adequately. Do you think Japanese fighters could have won the Pacific Air War with different design choices? Suzuki paused before answering, considering the question carefully. No, not with different aircraft design alone. The fundamental problem was production capacity and pilot training. America could build fighters faster than we could destroy them and train pilots faster than we could kill them. Even if our fighters had been equal to yours in capability, which they were not by 1944, we could not match your numbers. This was the essential truth that Japanese military leadership had been reluctant to acknowledge during the war. The conflict was not decided primarily by which side had better tactics or more skillful pilots or superior aircraft design. Those factors mattered, but they were secondary to industrial capacity and resource availability. The United States produced approximately 99,000 fighter aircraft during World War II. Japan produced approximately 30,000. The disparity was more than 3 to 1. Even if Japanese fighters had been significantly superior to American fighters in individual capability, which they were not, the numerical advantage would have been overwhelming. The Hellcat alone was produced in quantities that exceeded Japan's entire fighter production. 12,275 F6F Hellcats were built between June 1942 and November 1945. More Hellcats than all Japanese fighter types combined during the same period. Suzuki's examination of the captured Hellcat had revealed technical details about armor protection, self-sealing tanks, and robust construction. But the more fundamental revelation was about industrial philosophy. American industry could afford to build fighters with extensive protection because they had the resources and production capacity to do so. Japanese industry could not. In the decades after the war, military historians and aviation specialists analyzed the Pacific Air War extensively. The captured Hellcat examined by Suzuki received less attention than the captured Zero tested by American pilots. The Zero story was more dramatic, a complete, flyable aircraft that revealed exploitable weaknesses leading to placers, tactical advantages. The Hellcat story was more sobering, a damaged aircraft that confirmed what Japanese engineers already suspected. American fighters were built to standards Japanese industry couldn't match. The test panel bearing 20mm shell impacts became a symbol of industrial disparity rather than tactical revelation. But for the pilots who flew against Hellcats during the war, Suzuki's report provided valuable information. They understood that cockpit shots were less likely to be immediately fatal. They knew to aim for different target areas when possible. They recognized that American pilots had advantages beyond skill and tactics. Some Japanese pilots credited this knowledge with helping them survive engagements they might otherwise have approached incorrectly. The captured Hellcat's ultimate contribution was not tactical or technical, it was psychological. Japanese pilots needed to understand that they were facing not just skilled opponents, but opponents, protected by superior technology and industrial capacity. That understanding didn't change the outcome of the war, but it helped pilots make more realistic assessments of their chances and choose their battles more carefully. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.